Methods of hardening and tempering steel by heat treatment have been known to craftsmen for centuries. Today, a large number of industrial products and components are made of steel, hardened either as a whole or in part. A steel file is made very hard indeed, so hard it is brittle. It is easily fractured. Most tools used for cutting softer steel must be tough as well as hard, so that they don't fracture under fluctuating stresses. Hardness is combined with ductility. And sometimes other properties are needed in hardened steel, such as those of a spring. The extent to which steel may be hardened, the methods used, and the final properties all depend on its composition when it is first formed at the steelworks, particularly its carbon content, and also the addition of alloys, if any. After it is formed, steel is allowed to cool slowly, and because it cools slowly, it does not harden. Here is a diagrammatic section of a steel ingot at a high temperature, say 850 degrees centigrade. It contains atoms of gamma iron and atoms of carbon which form a solid solution known as austenite. When the steel is allowed to cool slowly, the gamma iron changes to alpha iron, which holds only a small quantity of carbon in solution. Most of the carbon combines with iron to form iron carbide, known as cementite. The remaining solution of carbon in alpha iron is called ferrite. These two substances form in alternate layers, and the structure is called pearlite. If we apply pressure to pearlitic steel, the layers can slide over one another so the steel will bend. It is unhardened. These steel billets are reheated at a rolling mill so that they can be rolled into a variety of cross-sectional shapes required by manufacturers. After rolling, the steel is again allowed to cool slowly. Some customers want their rolled steel hardened and tempered before it reaches them, and these consignments are transferred to the heat treatment shop. In this shop, steel is treated in large batches, weighing from 35 to 50 hundredweights at a time. The first step is to heat the steel in a furnace so that the pearlitic structure is changed back to austenite, the reverse of what we saw in the diagram. The batch is left in the furnace for sufficient time for the heat to transform the structure of the steel right through. When removed from the furnace, the batch is placed on a cradle above a large oil-quenching tank in which 6,500 gallons of oil are kept at an average temperature of 45 degrees centigrade by circulating it through a water cooler. Hot steel is now plunged into cold oil. The object is to cool the steel fast. We now want to see what happens to the structure of the steel when it is quenched. Gamma iron changes to alpha iron as before, but because the cooling is so rapid, the carbon does not separate from the solution, and we finish with a supersaturated solution of carbon atoms trapped among crystals of alpha iron known as martensite. The steel is extremely hard, in fact too hard, too brittle for most purposes. The brittleness can be relieved by tempering. The steel is reheated in the tempering furnace to a much lower temperature than before, depending on the composition of the steel and the properties required. Martensite is unstable, and on heating it begins to break down into ferrite and cementite, but they are not in layers. Fine granules of cementite are dispersed among the ferrite. This structure is retained on controlled, slow cooling, and the tempered steel is less hard than it was, but a lot more ductile. But how hard is it? How ductile? A sample is cut from the batch and sent to the testing laboratory. A section is cut from the sample, and standard test pieces are prepared. Hardness can be measured on this instrument, in which a 10mm steel ball of extreme hardness is impressed into the surface of the test piece with a standard load of 3,000 kilograms. The diameter of the impression made by the ball is measured. The smaller the impression, the greater the hardness of the steel. This machine tests the tensile strength of the hardened and tempered steel. Other properties are also checked. First, the extent of elongation, then the reduction of cross-sectional area at the point of breakage. There is also an impact test. The test piece has been notched in 3 places at mutual right angles. It is tested at each notch in turn. And if readings show that the resistance is similar at each point, it follows that the properties are even throughout the test piece. Since the properties of the steel depend on its composition, as well as the heat treatment, it may be necessary to check the composition directly in the spectroscope. Test standards having been met, the customer can now be assured that his consignment meets his specification. These are forged steel crankshafts about to be hardened by heat treatment. All the crankshafts look the same, but in fact some are made of a plain carbon steel, while others are made of an alloy steel. Furnace temperature is 850 degrees centigrade. Here is a batch of plain carbon steel crankshafts about to be quenched. It is poised above a tank containing cold water. The crankshafts remain in the water for only 3 minutes. Then they travel into the tempering furnace, which is controlled at 550 degrees centigrade. Next to the water quenching tank at the end of the furnace is another tank containing oil. The next batch of crankshafts is made of alloy steel. These are quenched in oil for a longer period, 9 minutes. What is the difference between oil and water as quenching media? Here is a simple demonstration. The jar on the left contains water, that on the right, oil. We shall quench 2 identical test pieces from the same temperature. The sample in the water is enveloped by a blanket of vapor which quickly breaks up, allowing water into contact with the metal. But the sample in the oil bath is still surrounded by the vapor blanket, and cooling is slow, until this breaks up. You see it happening now. So cooling in water is more rapid in the early stages and continues rapidly right down to 100 degrees centigrade. Since oil stops boiling at a higher temperature, cooling in oil is again slower during the final stage, when the steel actually hardens and when stresses may occur. Here is a section of steel after quenching in water. It shows numerous cracks which weaken the structure, the result of rapid quenching, which may also distort the metal. The same steel after slower quenching in oil shows no cracks or distortions. Further comparison may be made by tests on the crankshafts which we have seen being quenched, some in oil, some in water. Sections have been cut from both kinds of steel, and a Rockwell test shows that in each case the degree of hardness falls off towards the center of the section. But the fall-off in hardness in the water-quenched steel is greater than in the case of the oil-quenched steel. Why? The question takes us to the heart of the theory of heat treatment. In this laboratory, they are finding out the times at which transformation takes place in steel when it is quenched to a series of different temperatures, from the austenitic state down to the martensitic. The object of these experiments can best be understood by watching the results plotted in graph form. We plot temperature against time. Above its critical temperature, the steel is entirely austenitic. The sample, in this case a plain carbon steel, is quenched in a hot lead bath, only as far as, say, 680 degrees centigrade, and is then held at that temperature. After a period of time, the austenite begins to transform into ferrite and cementite. After a further period, the transformation is complete, and the steel will not harden when it cools. The same sample of steel is reheated, and again it is quenched, this time to a slightly lower temperature. And again we plot the times at which transformation begins and ends. This is done over and over again down the temperature scale till we reach the point at which the formation of martensite begins. After this point, the steel will harden, but only if it has not had time to transform at any higher temperature. By linking the points, we obtain time-temperature transformation curves for this plain carbon steel. Now let us plot the cooling rate of water on the same graph. Cooling in water is so rapid that there's never time for unwanted transformations. But when we plot the slower cooling rate of oil, we see that between about 600 degrees and 500 degrees, some transformation into ferrite and cementite takes place, though it will not be completed. Only what remains of the original austenite will harden. Now suppose the same experiments are conducted with an alloy steel instead of a plain carbon steel. The transformation times are retarded, as you see, so the alloy steel can be quenched in oil, thereby avoiding the possibility of cracking or distortion, and without unwanted transformations. It follows that if we find the transformation curves for any steel, we can see whether it may be quenched in oil or water. Many components today are made of alloy steel which can be quenched in oil. But since alloy steels are more expensive than plain carbon steels, the choice depends on economic as well as technical considerations. Meantime, research goes forward into means of extending the range of quenching oils by the use of additives. Again, the result may be seen on our graph. Rate of cooling is faster in the initial stages to avoid transformations, but it slows down like that of ordinary quenching oil at the lower temperatures when hardening takes place. Accelerated quenching oils can be used to quench lower carbon steels without cracking them, or to obtain greater depth of hardness in more expensive steels. Now let us apply theory and research to the reality of the shop floor, and also look at one or two variations in the process of hardening steel. This factory produces small precision tools. These drill chucks are intended for heavy industrial use. They are made from medium carbon steel, 0.4%, and have been through hardened in the usual way. But the factory makes another model as well for the do-it-yourself market, the spare-time handyman. Made from lower carbon steel, they are subjected to a specialized form of heat treatment. Each kind of steel is color marked for identification. This steel has a very low carbon content, only 0.1%, which means it is not suitable for hardening at all as it stands. However, it is less expensive to buy and easily machined. Production is rapid and economic. These are drill chuck sleeves, and the steel must be hardened in spite of its low carbon content. Here is how it's done. Propane gas is cracked and then fed into a furnace with ammonia gas. The components, placed on a shaking hearth conveyor, are fed into the furnace with its controlled atmosphere. Carbon from the propane and nitrogen from the ammonia are absorbed into the surface of the steel, thus raising the carbon content and introducing nitrogen at the surface only. The chuck sleeves are then quenched in oil. The tank can be clearly seen in this older type of apparatus, and the steel is hardened at the surface only. The process is known as case hardening, and when an ammonia-containing carbon-rich atmosphere is employed, the method is known as carbonitriding. Another method of case hardening is to pack the components among carbon granules before heating in the furnace. This is known as pack hardening. Yet another method is by immersion in a cyanide salt bath. It so happens that the production of case-hardened drill chuck sleeves illustrates one more variation on the process of heat treatment. The oil quench tank is lined with vertical bars. They're electric heating elements. They keep the oil at a temperature of 140 degrees centigrade. So the components are quenched not in cold oil, but in relatively hot oil. Here's the effect in graph form. Cooling ceases after hardening has begun, and the temperature is stabilized at this point to minimize distortion. This method is called Marquenching. The rate of cooling may be controlled at different temperatures to minimize distortion, or to produce special properties in the hardened metal. Here is a hardened steel component which has special properties and performs a vital function. It holds the rail to the sleeper with a force of 3/4 of a ton. It must also control a movement of 1/100 of an inch above and below the norm. The fasteners are made from rolled steel with a medium carbon content, 0.5%. It is an alloy steel containing silicon and manganese. This composition, subjected to appropriate heat treatment, produces the spring-like properties. As we follow this last example of heat treatment, we will recap on the theoretical points that have been made. Firstly, the structure of unhardened steel after slow cooling is in alternate layers of ferrite and cementite. The rods are carried through the furnace on a walking beam conveyor. Furnace temperature is 920 degrees centigrade. On heating, the perlitic structure breaks down and the steel becomes austenitic, carbon dissolved in gamma iron. The forming process is carried out rapidly between furnace and quench. The drop in temperature in the steel is only about 20 degrees centigrade. At 900 degrees centigrade, the fasteners are thrown into the quenching tank. Oil in the tank is kept cool by circulating it through a spiral tube cooling grid. The flow of oil is 5,000 gallons an hour. The oil is also kept free of impurities, first by passing it through a coarse screen filter, and then by passing it between magnetic discs which collect metallic fragments and particles. And so, during 15 minutes in the cold oil quenching tank, austenite is transformed into martensite, a supersaturated solution of carbon in alpha iron. It is now very hard, but also brittle. So after quenching, into the tempering furnace for 1 hour. The temperature here is critical, 530 degrees centigrade. Brittleness of the martensite is relieved by the formation of cementite in scattered granules. The additional effects of the alloys are not shown here. After leaving the tempering furnace, the fasteners cool slowly in air and retain the properties induced by heat treatment. They are now medium hard with a high tensile strength, 85 to 95 tons per square inch. Every mile of railway track requires some 8,500 fasteners. A sample is taken at regular intervals to be tested to destruction. It is vibrated at a rate of 1,000 cycles per minute. It is required to withstand 5 million cycles without fracture. Just one more example of the many uses of hardened and tempered steel.